Okay, yeah. I think we have a steady number of participants now. So good morning or good afternoon, good evening, depending on where you are. So welcome to the Journal Club for Physical Review Fluids by the American Physical Society. I'm Adrian Lozano Duran. I'm an assistant professor at MIT, Aeroastro. I'm also a editorial board member for Physical Review Fluids. And today is a pleasure to present this very interesting work on the investigation of the rough wall turbulence over Barnacle roughness. The presenters are going to be Sotirios and Angela, and I think that both of them are going to be contributing to the talk. A few words before we start. So the format is going to be a 15 minutes presentation. So we are going to have then time for questions at the very end. So the way that's going to work, when at the very end, even during the talk, you can write a question in the chat, but then for the rest of the questions, we'll take care of all of them at the very end. And in that case, you can either keep writing in the chat and I'll take care of the questions, or then you can just raise your hand and I'll just invite you to unmute yourself, and then you can ask the question. And we are going to allocate another 15 minutes for questions. So with that being said, I'm going to just open the floor to Sotirios and Angela to start the presentation, and I hope you all enjoy.
So thank you very much for the introduction, and thank you also for the invitation to give a talk at the Physical Review Fluids Journal Club on our paper. So in today's talk, we will first go over the wider background of marine biofouling and the different forms of fouling that can affect the surface. We will then discuss how we created the artificial barnacle fouled surfaces, which we investigated in our direct numerical simulations. When discussing the results, we will focus on the effects of the surface on the mean flow, and further statistics such as Reynolds stress and dispersive stress statistics can be found in the paper. Now, in the last part of the talk, we will briefly discuss the blanketing layer which forms over the rough surfaces and which has yielded some unexpected results. I will hand over to Sotirios, who will give a brief introduction to marine biofouling.
Thank you, Angela. So we find many types of roughness in marine environments. For example, roughness can be caused by corrosion from salt water. Cavitation damage can be found on fast-moving ship parts such as propellers and hydrofoils. And of course, manufacturing imperfections may be present such as welding seams and paint imperfections. A very important class of roughness is marine biofouling, which is caused by the accumulation of marine organisms on surfaces submerged in seawater. The organisms most found on marine biofouled surfaces are slime, algae, and of course, hard-shelled ones like barnacles, turbulence, barnacles, turbulence, mussels, etc. All these types of roughness can have an impact on the efficiency of vessels or machinery that operate in a marine environment. However, marine biofouling is probably the most pervasive form of marine roughness. Biofouling has both substantial economic and environmental impact. A major effect of biofouling is the increase of friction drag on surfaces submerged in seawater. This is important because friction drag can amount to 80–25% of the total resistance of typical merchant ships. This has consequences for the environment. In 2021, the shipping industry contributed approximately 3% of anthropogenic CO2 emissions. Operators of ships also experience substantial economic impacts. According to the Clean Shipping Coalition, fouled hulls cost the shipping industry as much as $30 billion per year. Michael Schultz estimated for a typical ship of the US Navy that the operational cost for a single ship can increase by several $1 million per year depending on the fouling rating. The highest fouling ratings are associated, of course, with calcareous macrofouling. This is why we selected fouling by barnacles for our study, a typical form of calcareous macrofouling and one of the most persistent. To be able to generate realistic barnacle fouled surfaces, we have developed an algorithm that mimics their settlement behavior. To understand how this algorithm works, I will first describe how barnacles decide where to settle on the substrate. So barnacles begin their life as nauplius larvae. They swim around, eating plankton, gathering energy for the next important step in their life cycle, that of the cyprid larva. During this period of their life, barnacles swim towards the substrate, essentially walking on their two front appendages, searching for a suitable place to settle. They prefer to settle near other mature barnacles, as this indicates that the place is full of nutrients, good molting conditions, and good chances to reproduce. After finding the appropriate place to settle, they become sessile, first undergoing their juvenile state. After that, they form calcareous outer shell and continue to grow to their mature stage. At this point, they can reproduce and continue the cycle. In our algorithm, we considered only mature barnacles and we simplified their shape to a conical frustum for our simulations. Now, our algorithm for the generation of artificial barnacle surfaces has the following basic steps. First, we select the total number of barnacles. Some of these barnacles will be defined as seed barnacles, which will form the nucleation sites for the barnacle clusters. In the next step, the geometric characteristics of all barnacles, that is their radii and heights, are defined based on realistic random distributions. Then the seed barnacles are placed randomly on the surface. Each of the remaining barnacles is then placed in turn in the vicinity of a randomly selected barnacle that has already settled on the surface. The algorithm stops when all barnacles have been placed or there is no more room for other barnacles to be fitted. The algorithm allows us to control the coverage, the degree of clustering, and the number of clusters on the surface. So now Angela will explain the rough surface we used for this study and the simulation setup.
Now, over time, a surface affected by barnacle biofouling will be typically covered by more and more barnacles. To mimic this behavior, we have settled more and more barnacles on a surface to vary the coverage from 10% to up to 85% when we could not place any more barnacles on the surface. We can now group these surfaces into three categories. For the low coverage states, we see distinct barnacle clusters. For the intermediate coverage states, the clusters start to merge. Instead of distinct clusters, we are then just left with some bald patches. Finally, for the two highest coverages, the entire surface is covered by barnacles and we have effectively uniformly random covered surfaces. Now, in this table, some of the topographical parameters of the surface are summarized. Now, all surfaces have the same maximum barnacle height. This we achieved by ensuring that the highest barnacles was already present on the 10% coverage surface. The frontal solidity of the surfaces increases as more and more barnacles are placed on the surface. Skewness and kurtosis of the height distribution decrease with increasing coverage. When we plot skewness against kurtosis, we can see that as the coverage increases, the skewness drops to a near Gaussian value. Now, in our simulations, we ran direct numerical simulations to obtain the fluid dynamic roughness effects of all surfaces. These were conducted at RE tau of 395. We used periodic boundary conditions in the streamwise and spanwise direction to have a turbulent channel flow setup. This is the setup as most efficient configuration for DNS of rough wall turbulent flows. The roughness is applied to both sides of the channel to preserve the statistical symmetry of the flow. The roughness was resolved using an iterative embedded boundary method based on the method by Young and Balleras. To be able to resolve the flow in the gaps in between the barnacles, we had to use a very fine mesh in the streamwise and spanwise direction. Now, in the next part, Sotirios will talk about how the mean flow changes with increasing coverage.
So the first output that we get from our simulations is the Hammer roughness function. This is defined as the downward shift in the mean streamwise velocity profile of a rough wall case compared to the smooth wall equivalent at the same friction Reynolds number. In the two plots shown on this slide, we plotted the roughness function of all the rough surfaces against their frontal solidity and their effective slope. The roughness function at first increases with increasing frontal solidity, which also means increasing coverage, up to the case with 60% coverage. For higher coverages, sheltering effects take place and the roughness function value decreases. We find a similar behavior as reported for studies on regular forms of roughness. The frontal solidity and the effective slope are directly related. The results from other studies plotted in the right plot involve different types of roughness with increasing effective slope, but approximately constant skewness. In many studies, a saturation of the roughness effect at an effective slope value of approximately 0.35 has been found. This effect is not evident in our results. One factor for this difference is that for our barnacle surfaces, skewness decreases as the effective slope increases. Now, if we observe the time average streamwise velocity field at a near the wall location, that is at 30% of the maximum barnacle height, we can see that the flow behavior can be classified into three distinct categories. In the top row, we have surfaces with low coverage. In this case, we have distinct barnacle clusters with large areas of smooth surface in between. Here, the flow can attain high mean velocities over the smooth surface areas, while the barnacle clusters form obstacles with relatively large areas of recirculation at their way. In the middle row, we have surfaces with medium coverage. In these cases, the barnacle clusters have connected, leaving some areas of smooth surface in between them. Here, the velocity over smooth surface patches is not as high because the increased blockage of the near wall flow by the barnacle weakens their recovery. In the last row, we have surfaces with high coverage. Here we observe low mean velocity values between the roughness elements because the outer flow skims over the rough surface. We can still see some channels with higher velocity in between barnacles, but there are, of course, of lower magnitude compared to the flow over surfaces with low coverage. This categorization of flow is similar to urban canopy flow as observed by Oki in 1988. They also identified three categories of flow over urban canopies with increasing density. They named them isolated roughness flow, wake interference flow, and skimming flow. Angela, back to you.
Now, in the final part of the talk, we will characterize the effect of the rough surfaces on the outer flow, that is the flow above the rough surface, using the blanketing layer. Now, what is the idea behind the blanketing layer? In the case of a smooth wall flow, we have a viscous sublayer where we see a linear law for the mean velocity profile. In the case of a rough wall flow, we know that for very low roughness side, Ks+, the flow behaves hydraulically smooth and the roughness is effectively submerged in the viscous sublayer. Now, as we increase Ks+, the roughness starts to significantly alter the near wall flow and roughness effects on the mean flow start to become visible. Now, once we enter the fully rough regime, the roughness effect dominated the entire near wall layer and the mean flow becomes independent of the Reynolds number. Now, the question is, what replaces the viscous sublayer and how does the outer flow and its flow above the rough surface perceive the roughness? Now, to look at this, we use the concept of the blanketing layer, which is defined as a single connected surface where the time average streamwise velocity reaches a value of 5 in plus unit. Now, for a smooth surface, the blanketing layer would simply be a plane which is offset by 5 plus unit relative to a smooth wall. Now we can, for a rough surface, the blanketing layer for a rough surface, the blanketing layer is implicitly defined and needs to be found numerically from the time average flow field. For our present cases, the blanketing layer looks like this. We can observe that for the low coverage states, the blanketing layer wraps around the barnacle clusters, but is still largely flat over the other sections of the surface. For the intermediate coverages, this starts to change, and the blanketing layer starts now to shift more towards the top of the roughness elements, but it still dips below this level over the remaining blank patches of the surface. Finally, for the highest coverages, the blanketing layer increasingly flattens and is dominated by elongated structures which remind me of fish scales. The barnacle structures below cannot really be discerned anymore. Now, using the cross correlation between the blanketing layer and the height map, we can quantify how well the blanketing layer can conform to the underlying rough surface. We see that this cross correlation factor decreases with increasing coverage and eventually becomes approximately constant. We can further quantify the blanketing layer by characterizing it using topographical parameters, which we just define in analogy to the parameters to characterize a rough surface. We can, for example, see that the skewness of the blanketing layer height distribution becomes negative for the medium coverage states, where the blanketing layer dips down over the remaining bald patches on the surfaces. We can also see from the ratio of the streamwise to the span-wise correlation lengths of the blanketing layer that these strongly elongated structures form for high coverages. Now, finally, we can also observe that the frontal solidity of the blanketing layer increases for small coverages, but then decreases as the blanketing layer increasingly skims above the rough surface for high coverages. Now, this observation gave us the idea to revisit our earlier results for the roughness function. Now, when we plotted the roughness function against the frontal solidity of the roughness, then we saw first an increase and then a decrease at high frontal solidities. Now, to our surprise, if we instead plot delta U plus against the frontal solidity of the blanketing layer, we see an approximately linear increase with the frontal solidity of the blanketing layer. Now, the blanketing layer effectively helps us to understand why we observe a decrease in the roughness function at high frontal solidity. This is because the flow above the rough surface effectively perceives the surface as less rough, since the flow starts to increasingly skim past most of the roughness features. Now, to summarize, the barnacle surfaces we have investigated can be considered as a form of hybrid roughness because they are composed of roughness elements like regular rough surface, but on the other hand, they are irregular and inhomogeneous surface because we have a distribution of element sizes and we have an irregular clustered arrangement. Now, in the present talk, we have focused mostly on the roughness function and how this relates to the surface topography in the blanketing layer. In our paper, we also discuss some further statistics. Before I conclude, I just wanted to briefly put up the list of references for the papers we have cited in this talk. And I would also thank our collaborators and research funder, EPSRC, and access to the UK's National Supercomputer Archer for this work. Thank you for your attention.
Okay, yeah, thanks a lot, Angela and Sotirios, for the presentation. Also, thanks for trying to be on time. So now the floor is open to questions. You can just raise your hand if you want to ask a question. Also, feel free to use the chat. You can write in the chat and then I'll read the question back. Okay, so before, while you think about the question of people, in case you are still a bit shy, I wanted to ask a question about this solidity that is revisited. So you show that with the new definition of solidity, you can actually have a function that looks very linear, like the shift in the mean velocity profile is very linear. I was thinking if you think that this could be applicable to other types of roughness, and in particular, I'm thinking of modeling. Like, imagine we don't have like a high fidelity data. I just know some the geometry of the surface, and then I want to estimate what is going to be the shift in the velocity just from the geometrical properties. So you think that this could be used as a way of like the venue for modeling, not only this particular type of geometries, but other types of geometries?
Well, first we just have tested this for this particular set of rough surfaces. So it needs to be first determined on whether this holds for other rough surfaces. And it's very likely that this is not the only parameter that will affect the roughness effect. So, but yeah, and then the second question is, we would need to, as currently we find this solidity of the blanketing layer from the time average flow field. And of course, we need to have these direct numerical simulations to get this. So for the modeling approach, we would need to find a way to predict this blanketing layer based on the surface topography of the surface. So the question is, could we define equations as mimics this behavior? I don't know. I mean, I haven't tried yet, but for example, could we define a modified sign distance function and find equation for that? That would be based on the topography. But yeah, that is speculative whether that's possible or not.
Yeah, I had in mind something like, you know, in LES, where such that the grid size, so the roughness is completely subgrid. So you cannot resolve anything at all of the roughness, but you know what type of roughness you have. And ideally, it's not only the shift in the mean. Actually, what you would like to know is the stress at the wall effective that you will get. I suppose that this is something people investigate a lot how to, but because your relationship that you show seems to be so clear, like the shift in the mean, that looks like it would be very intuitive to use that as an estimation of what should be the stress at the wall, maybe. Okay, so yeah, if you have any questions, just raise your hand or just feel free to use the chat. Yeah, so James, go ahead.
Yeah, very nice talk. Could you please talk a little bit more about the immersed boundary method that you use in the resolution of the individual roughness elements, and whether you tested accuracy? I mean, this really isn't a DNS since you're using the immersed boundary method. There's a modeling component to it. So could you talk about that a little bit more, please?
Yeah, so we did conduct a grid refinement study on this 10% surface was our example for this, and we determined that with that grid spacing, we were getting grid independent results for from this method. So this immersed boundary method, or it's an embedded boundary method, has also been tested earlier against other data where we, for example, had wavy surface, where we had the data from a grid conforming methods from the literature, and we could also match these results, their results with this method. So it has been validated against the method itself, against independent data in the literature, both by the original inventors of the method, and then when we applied it to in our code, we validated it.
All right, thanks. Could you just say typically how many grid points in the horizontal covered one of your barnacles?
A specific barnacles. So we, if you look at the total number of grid points in the streamwise direction was 864, in the spanwise direction 432. So we would have to think about what exactly was the size per barnacle. So yeah, I don't remember the Sotirios. I don't know whether you remember this.
I don't remember the number right now. I can look it up, and maybe if you share your contacts, I can send an email with.
Oh, it's okay. It was just a curiosity question. Is it of order 10?
Yeah, it should be I think of the order of 10.
Yeah.
All right. Thank you.
So a follow-up on that question that James was asking, so that you're using the immense boundary method. So what would be the alternative if you don't use that? For yes, use an unstructured solver to.
Yeah, I guess it would be very difficult to get any kind of regular grid for these type of surfaces. So I think, yeah, effectively unstructured, maybe polyhedral mesh or something might work, but we haven't tried this.
Well, I mean, if the surfaces were had a regular arrangement of barnacles, we could use some form of structured mesh, but in these cases, I think that it's very difficult.
In this case, it's not regular, the structure, so you cannot use a mapping. Change of coordinates will give you a flat surface. In this case, you really need to use inverse boundary.
Exactly.
I suppose something like something like an unstructured grid, but that will probably imply an overhead in the resolution that you're going to need and the cost of the simulation.
Yeah.
Okay, we have still like a few more minutes. If someone else wants to jump in and ask a question, or again, use the chat.
Oh, okay. So I have a question from Shaheen.
Okay, I couldn't see that, so probably was.
No, it's directed to me.
Okay,
actually.
okay.
So,
if you have any other questions, just write it in the general chat so I can also look at them. But okay, go ahead, please. Just read the question and go ahead.
So you showed a graph of ship costs as the age of the ship increased. Is that all costs or just fuel costs? So I think that's all costs. Is it? That's the Michael P. Schultz graph.
Yeah, I believe so. That was the fouling rating basically, and I believe he estimated the total cost, maintenance, and increased fuel consumption. So if we go back to that slide. So here, well, that was his fouling rating, and that was the annual additional cost compared to a smooth hull associated with maintenance and increased. I think the main thing was increased fuel consumption.
Okay, we have another question in the chat by Justin. So he says, well, thank you for the talk. And I was wondering if you consider what might occur if the surface with a higher frontal solidity were held within the transitional rough regime. Would the streamwise Reynolds stresses for the higher coverage surface behave more like a 10% or 15% surfaces where the inner peak is more prominent?
So if we held the highest coverage state in the transitionally rough regime, so what happens to the Reynolds stresses, streamwise Reynolds stresses? So I would believe that we still would see the dominant effect for the Reynolds stresses for the high coverage state always associated with the tops of the roughness elements, because they have the strongest interaction with the flow past it, and such we would expect there to have the strongest streamwise Reynolds stresses occurring there. Now, the very low coverage states, for them, we have still some of the smooth wall behavior left, where we would expect the streamwise Reynolds stresses to peak very close to the wall above the smooth section. But of course, we also have the roughness elements, which also interfere and then have more peak that is associated with the sort of crest of the roughness element. So there we have, for these very low coverage states, we have a double peak structure. And so I think for the high coverage state, whether they are transitionally rough or fully rough doesn't really matter to where the Reynolds stress peak occurs. It will be always, in my opinion, associated with the crest of the roughness, but we haven't tested this systematically. So that's just here based on our understanding in general of these rough surfaces.
All right, and we have one last question by Frank. Is there an estimate of typical surface coverage for the ships in service?
Well, this depends entirely on how much is spent on maintenance and also in what they are exposed to and how good the hull is prepared. So I can't give a figure for that, but I recently read an article where they claimed that due to COVID, a lot of ships were not active for some time and not really maintained. So now we have higher coverages typically than pre-pandemic, and now they need to catch up with maintenance of these hulls. But so it depends on a lot of circumstances of what the ship hull looks like. Okay, very good. So I think that we are just right on time. I want to thank again Sotirios and Angela for the talk. I think it was very interesting. I actually might reach out to you later to ask a few more questions. I also invite the other people to do the same if they feel like. So with that, we are closing the Journal Club today. I also want to thank all the participants for joining, and I suppose I'll see you for the next Journal Club. So thanks to everyone. Thank you.